How do you solve the energy storage problem? Listener Stephen Gubkin asked me that in July. That's when I realized that I should have scheduled the energy episode much sooner in this series, like maybe in the first 5 shows. I was trying to balance technical and social topics, but I should have prioritized energy because it could be the tall pole for the reference design. I used to live in fear of the dreaded tall pole back when I worked for an aerospace design company in California. Think of a tent. The poles holding it up are your constraints. The fabric covering it is your design. As a designer, you want the fabric to cover all the poles. But there's always the possibility that when you get into the details, one of the poles might turn out to be too tall. That's when, no matter how much you stretch it, your design cannot cover one of the basic constraints, and it fails. Is energy storage a tall pole? Well, when we're talking about replacing all fossil fuels with solar energy in today's economy, then absolutely yes, for reasons I'll get into in a moment. But Edenicity doesn't just replace fossil fuels with solar power. It also redesigns everything so it's way more efficient and convenient. We're not driving cars anymore. We're not eating the same way, or heating or cooling or arranging our homes or our work environments the same way anymore. And a curious thing happens when our design tent covers many more aspects of our lives. It shrinks the constraints themselves again and again until they're easier to cover. Then we really have something worth building. Cities designed like modern Edens for economic and ecological abundance. I'm Kev Polk, your guide to Edenicity. Welcome to episode 32, where I'll discuss the Edenicity of energy. I won't keep you in suspense. Here's why energy storage is the classic tall pole of renewable energy. I'm just going to use solar energy for today's discussion because that's the sole power source I used in the Edenicity reference design. See the show notes to download a copy. Solar panels require ways to store energy for those times when you need power, but there's not enough sunlight. Now, we could just do what's done today and keep some of those fossil fuel and nuclear power plants active and run them as needed to cover any shortfalls in solar power. But if we did that, we'd still have a lot of carbon emissions and nuclear wastes to deal with. That defeats the whole purpose of Edenicity. Or we could use other renewables such as hydro, biofuels, and wind to fill in those solar gaps. There's studies that say this would work, but it would be complicated. To make Edenicity easy to build, I'm looking for something simple that can be implemented at both small and large scales. So we're back to pure solar power plus storage. Gubkin sent me a link to a dothemath.com article that tackled the energy storage problem way back in 2011. The article supposed that we could use the cheapest battery technology available at the time, lead acid. Then it calculated how much lead we would need to store 7 days of energy at the current U.S. consumption rate. Let me stop right there and point out that I don't know how realistic 7 days storage is. That would depend on detailed climate and weather modeling for the construction site. But based on several years of personal experience with off-grid living and home building in Ohio, I'd say 7 days is too high. But let's go with it for now, just to build in an extra level of security. The result? The United States would need 30 times more lead than the world's current reserves, and 60% more than the total we could expect to mine anywhere in the world. Lead's scarce. Who knew? And that's just for the United States, which houses just 4.3% of the people in the world. To supply the current global population at current U.S. consumption rates, we would need 23 times more lead for those batteries than we could mine anywhere in the world. But 2011 was a long time ago. What about more advanced batteries, such as lithium-ion, that power electric cars? Well, the article goes on to point out that lithium, nickel, and other materials used in those batteries are scarce too. The article provides the numbers for the world reserves of these materials, but it doesn't examine how much of these are needed for advanced batteries, nor how efficient these batteries are. Not to worry, I looked up the components of lithium-ion batteries in Chemical and Engineering News and did the math. Suffice it to say that if the whole world consumed power like the United States does, we'd need about 5 times more lithium and 16 times more nickel than we could expect to mine anywhere on Earth. Bottom line, it would be very hard to build enough batteries to power the whole world with 100% solar energy, given the assumptions in the dothemath.com article. Fortunately, those assumptions don't apply to Edenicity, because Edenicity cuts energy demand by an astonishing 98.4%. I'll explain how in a moment. That means that even when 10 billion people live in Edenicities, 7 days of lithium-ion energy storage would only require 12% of existing global lithium reserves, 4% of copper reserves, and 41% of nickel reserves. In other words, we can build Edenicity without having to find any new material for batteries. It exists, and we know how to get it. Better still, with no cars, Edenicity will shrink demand for most metals and other industrial materials to the point where most or all of them can be obtained through recycling the soon-to-be obsolete infrastructure. This would leave us with millennia of reserves with no new need for mining. Even better than better still, there are many new storage technologies that promise more durability, lower cost, and greater safety than lithium-ion batteries. CCT Energy in Australia uses molten silicon to store solar energy as heat, and it can provide power while being charged. It's more compact, slightly cheaper, and much more durable than lithium-ion batteries. It's also fully recyclable. Energy Nest in Norway uses heatcrete, which is a form of concrete, to store heat energy for industrial applications, and it claims to be up to 47 times cheaper at storing energy than lithium-ion. To get a sense of how much energy the reference design saves, think of all the things in your life that use energy: light bulbs, chargers, stoves, washing machines, furnaces, air conditioning, cars, sound systems, plus all the industries that manufacture the clothes you wear, the car you drive, your furniture, the house you live in, the streets you drive on, the gadgets that grab your ears and eyeballs, and the equipment that processes and delivers the food you eat. Now imagine being told that you could only use all that stuff for a total of 12 hours in a whole month. Can you see how futile it would be to trim your personal energy consumption down by 98.4%? But that's the power of comprehensive large-scale design. Not only is it possible, it's easy with Edenicity. Here's how Edenicity cuts energy consumption by 98.4% while increasing our quality of life. According to a summary of U.S. energy use in 2019, released by Lawrence Livermore National Laboratory in March of 2020, energy consumption is split about evenly between buildings, transportation, industry, and energy lost in heat in electrical generators and power lines. While Edenicity has no generation and transmission losses because solar panels convert some of the sun's energy directly into electricity. On average, fossil fuels burn 3 units of fuel to get 1 unit of useful work. But the sun shines with or without solar panels, so solar energy is all gain and no loss. For my calculations, I'm stating the total system efficiency of energy conversion and transmission for solar power. Okay, what about transportation? Well, transportation uses 98.5% less energy than the status quo based on my analysis in episode 12. Instead of nearly 1 car per person like we have now, Edenicity would have 1 underground loop transit pod for every 812 people. Each pod would seat 16 and go 3 times faster than a regular car. Trips between cities would be by Hyperloop, also underground, traveling 4 times faster than the loop transit, which works out to over 1,000 kilometers an hour. These are hyper-efficient transportation systems because they don't burn fossil fuels, which waste 80% of their energy producing heat rather than motion. When loop or hyperloop vehicles need to slow down, their electric motors do something that internal combustion engines can't: operate in reverse. In other words, electric motors become generators, resisting the pod's motion, converting it into electrical energy so that it can be stored in a battery for later use. That saves another 64% or more of the energy. Together with the innate efficiency of electric motors, that's a 15-fold improvement over cars, and when you add the extra passengers per trip, even at 50% capacity, that gets you to that 98.5% figure that I mentioned. Buildings would be 95% more energy efficient than the status quo, for reasons I detailed in episode 9. This figure is actually just 37% more efficient than the townhouse I live in now, excluding heating and hot water, but including a very inefficient air conditioner. My building was built in 1970, and it has essentially no energy upgrades. That gives you some idea how much more efficient row or apartment houses are than the standalone homes that dominate the home energy statistics in the United States. A row of Edenicity houses would enclose 3 1/3 times more volume than the row of townhouses where I live, making them inherently 49% more efficient to heat. The walls, windows, and entrances would be up to modern insulation standards. The greenhouse roof would further buffer the climate. And even moderately high-efficiency modern heat pumps would provide heat, air conditioning, and hot water at more than twice the efficiency of my ancient air conditioner, more than enough to close that 37% gap. At the cutting edge of research today is a range of passively heated and cooled construction techniques. All involve extreme insulation, and I've toured a few myself. The goal of these passive houses is to require zero electrical power to maintain a comfortable climate year-round. These eventually could prove extremely durable. A certain fraction of Edenicity construction should be dedicated to making these techniques robust across a wide range of climates. Industry would use 97% less energy because Edenicity doubles the efficiency of energy generation in this sector and gets rid of cars, car infrastructure, and fossil fuel refining, all of which make up a surprisingly large fraction of industrial energy use. And again, Edenicity's transportation systems utilize 331 times less imported material, such as steel, and are built to last over a century, not the 8 to 15-year lifetime of a car. They would also save energy by being designed for complete recycling. In summary, Edenicity's comprehensive design achieves a 98.4% reduction in energy consumption, which would be impossible for an individual. The many efficiencies that Edenicity enjoys in the realms of construction, transportation, industry, and energy generation and transmission combine to cut total energy consumption by 98.4% while offering far more amenity than we're used to today. For example, that 4-minute commute that I mentioned in episode 12. Okay, but where are we going to get the solar power? Short answer, bike paths, industrial zones, roofs, and windows. Let's start with the bike paths. These are transparent roofs that provide shelter from the weather, plus overhead views, plus solar power. How? They would use transparent solar panels. There are multiple technologies to do this that are already available or in development. The common theme among them is that they convert near-infrared energy and sometimes some ultraviolet energy into electricity and let much of the visible light through, typically about 40 to 45%. These same transparent photovoltaic materials would also be used in greenhouse roofs and upper floor windows to provide power. In the case of the greenhouse roofs, of course, only a small fraction of the overhead area would be used for solar panels, so that the roof could let in enough sunlight for the plants to grow. Traditional opaque solar panels would be used in the 4 industrial zones, and these would have twice the efficiency of transparent panels, but cover about half the surface area of those zones. And amazingly enough, this meets Edenicity's needs even in Ohio in clear winter weather. There would be an excess of energy in the summer or throughout the year in locations located closer to the equator. The excess power could boost industrial production or be shunted to other cities along power cables that run along the buried Hyperloop paths or stored. This is the perfect opportunity to establish real-time energy markets to allocate the excess. Commercial and industrial consumption still accounts for 2/3 of energy use in Edenicity. In extreme inclement weather, these could be scaled back to extend the 7-day storage up to a month in relentless rain or snow, or 70 consecutive days of overcast weather. It would be prudent to build the first Edenicities in subtropical or tropical locations and link them to more temperate climates with Hyperloop tunnels that carry power lines. Now, did you wonder if there's enough material to build all those solar panels? Well, we won't run out of silicon anytime soon. Silicon, which is used in traditional photovoltaic cells, is the second most abundant element on Earth and the 8th most abundant element in the universe. 30% of Earth's crust is silicon. You can make transparent photovoltaic cells by drilling tiny holes in the silicon. A wide variety of substances can be used with silicon or even plastic to make solar cells. It's easy, it's profitable, and it's sufficient to provide all the solar energy people use on Earth, if we use ecologically sound design. So let's do the math. 10 billion people living in Edenicities would require 21 petawatt-hours a year worth of energy, 29 times more than all the solar panels in the world can produce right now. But the world's solar power inventory increased 35-fold between 2009 and 2019. It will probably increase a similar amount over the next decade. Therefore, even if we build Edenicity over the next 8 years, for everyone alive now plus 2 billion more people, a nearly impossible population explosion, we'll still have enough solar panels. Solar panels will not be the tall pole, and as we saw before, neither will energy storage. So if you know anyone who doubts that we can transition to green power quickly, tell them this. There will be enough solar power and solar energy storage coming online in the next decade to provide everyone in the world a much higher quality of life than the world has ever known, if we design our cities well. That's what I call power to the people, and that's the power of design. If episode 32 blew your mind, please let your friends know about it by clicking the social media share link in your podcast player. And be sure to join me next time when I'll discuss how immigration can make the world twice as rich. I'm Kev Polk, and this has been Edenicity.